into my journey. 1.2 light years from Earth. 26% of my acceleration phase complete. My speed is 13,000 kilometers per second. My fuel usage, 19%. I jettison my spent fuel cells. I am on course for arrival at Minerva in 31 years' time. Does life await me?
When I was about 10 years old, I had one of these department store telescopes, learned how to use it, took it out one night, and focused it on what I was told was the planet Saturn. And when I lined up the viewfinder and held it still, and I could see Saturn and its rings, at that moment, I felt a calling, and that calling was to learn about how to get there.
T-minus 10, 9, 8, 7, 6, 5.
Les Johnson answered that calling,
2,
becoming a world-leading expert in advanced concepts at NASA Marshall Space Flight Center. In 1999, he led pioneering research into interstellar propulsion.
Nature is kind to us in the regard to what options we're going to have to get to the stars. Nature has said, you smart people, you can figure this out. It's just going to be really hard. It was difficult enough to go to the moon. We're sending probes to the different planets in the solar system. But to take that leap to go to the stars, the distance is just so much further and requires so much more energy that it's just going to take some time.
The goal of engineering missions to the stars confronts explorers with distances they've never even contemplated before. 1 light year is over 9.4 trillion kilometers, which makes our nearest star over 40 trillion kilometers away. That's more than 1 billion round-the-world flights. According to the masters of solar system exploration, the greatest challenge is how to propel a spacecraft fast enough to travel light years within a lifetime.
In order to get humans to make the enormous effort required to fly that kind of mission, you need to have the period of time between when you launch and when you actually get information back be no longer than a typical human lifespan. Humanity has never launched multi-generational voyages of exploration. It's simply never been done. The distances are just daunting. And so there's going to have to be major breakthroughs, mostly in propulsion.
Chemical-fueled rockets like Saturn V have been the workhorses of solar system exploration. They got us to the moon in just 3 days. But to reach a planet orbiting our nearest star within a generation, we'd need to travel at a speed that covers the Earth-to-Moon distance in just 8 seconds. That's 17% the speed of light.
Chemical rockets are great for getting out of the gravity well. You have the high thrust to overcome Earth's gravity, but they're terribly inefficient. And in order to get to the stars in a reasonable amount of time, you're going to need to get up to some pretty high speeds. And it's not just the thrust, it's how efficiently you do that. Because if you're inefficient, you have to have a lot more fuel, and you get to a point where you can't carry enough fuel to move your own weight.
The capability of any propulsion system is governed by the rocket equation, a trade-off between thrust, efficiency, and weight. The most powerful chemical rocket in operation, Falcon Heavy, first launched in 2018, weighed 1.5 million kilograms at takeoff, and 95% of it was fuel. It burned through all that fuel in just 10 minutes in order to create enough thrust to deliver its unusual payload beyond Earth's gravity. Wherever Starman is going in his Tesla, it isn't the stars. Only one chemical-powered spacecraft has ever made the leap beyond our solar system. In 2013, 36 years after its launch, Voyager 1 entered interstellar space at 17 kilometers per second. Fast enough to travel London to Beijing in under 10 minutes. But at less than 0.0001% the speed of light, still painfully slow if you're aiming for the stars.
They're well beyond what's considered to be the physical boundary of the solar system. And it's taken over 30-some years to get there. At that speed, they'll take 70,000 years just to get to the nearest star. Now, chemical rockets aren't going to do it.
As the push for interstellar exploration gathers pace, the workhorses of the old space race are put out to pasture. Monuments to a bygone era. But if not chemical rockets, what will deliver the seemingly impossible thrust and fuel efficiency required to journey to the stars within a lifetime? 3 potential propulsion solutions are being explored today: fusion, antimatter, and plasma.
Alors imaginons qu'on veuille aller vers Proxima du Centaure, donc l'étoile la plus proche de notre système solaire, à 4,3 années-lumière. Et imaginons qu'on veuille y aller en quelques décennies. Si on veut utiliser un moteur de fusée classique, en fait, on peut montrer que la quantité de carburant qu'il nous faut, elle est supérieure à toute la masse de l'univers connu. Par contre, si on utilise un propulseur à plasma, eh bien, en fait, il nous faudrait simplement quelques dizaines ou centaines de kilogrammes de carburant. Donc là, la mission devient possible.
Physicist Stefan Mazouf is working at the cutting edge of electric propulsion. The Hall plasma thruster.
On part d'un carburant, plutôt sous forme gazeuse, on va l'électriser, et ces particules électriques, qu'on appelle des ions, vont être éjectées à très grande vitesse. C'est l'éjection de cette matière qui va faire avancer le véhicule spatial.
On va rentrer le moteur.
Since the 1970s, plasma thrusters have been used in satellites to make positioning adjustments while in orbit.
So he's coming up on 90 meters and closing.
Range is 70 meters and range rate 0.34.
Their principal advantage is efficiency, demanding just a tiny fraction of the mass of fuel required by chemical rockets.
Prenons l'exemple de la sonde Voyager 1, qui se déplace actuellement à 61 000 km/h. Avec un propulseur chimique classique, un moteur de fusée, on peut atteindre cette vitesse en quelques jours, mais en consommant 92 tonnes de carburant. Un propulseur à plasma utilisé aujourd'hui sur satellite permettrait d'atteindre cette vitesse, certes en 2 ans, mais en consommant uniquement une dizaine de kilogrammes de carburant. Cependant, si on embarque beaucoup plus de carburant, on pourra utiliser le propulseur pendant beaucoup plus de temps et donc au final atteindre une vitesse très supérieure à celle de la sonde Voyager 1, voire même atteindre une fraction de la vitesse de la lumière.
plasma engines offer hope of achieving the speed required to reach the stars. Still holding them back is how long it would take to achieve that speed, dragging the total trip time into thousands of years. But in the shimmering upper atmosphere of our own planet lies the potential for a kind of propulsion until now only dreamt of in the realm of science fiction.
I am the navigator. My mind is full of stars, and every planet and every moon. Every celestial body that is known, I know also. But the dangers my creators did not know of, I must discover for myself. An asteroid field. I turn to face it, head on. My titanium shield absorbs the impacts. But one stray penetrates my mind. My emergency backup command system activates. I am reborn. I re-engage. I journey on.
In 1995, at the CERN Particle Collider in Switzerland, for the first time in human history, scientists succeeded in producing the most efficient source of energy achievable within the laws of physics: antimatter.
As any good Star Trek fan will know, right, on the Enterprise, that's what powered their warp drive. Of course, warp drive is science fiction drive. But if you think about antimatter, it's real. Just like normal matter is protons, electrons, there are antiprotons and anti-electrons. When matter and antimatter come in contact with each other, they annihilate. And it essentially is the perfect E equal mc squared moment is released as energy. And therefore, it's the most efficient battery we can ever build, the most efficient battery that nature will allow us to have.
Antimatter is created naturally in space when cosmic rays collide with atoms in the Earth's atmosphere. Producing it at the CERN was a phenomenal scientific and engineering breakthrough that required accelerating particles to the speed of light and smashing them together. The challenge now is how to create enough of it to propel a spacecraft.
This is where it gets tough. If you look at the total amount of antimatter produced globally today, it's on the order of nanograms. You would need on the order of kilograms, perhaps up to a ton of antimatter to drive a starship. That's not something I want to do on the Earth, because the amount of energy released if that ton of antimatter met a ton of matter would be catastrophic. And so you're going to have to build the ability to, you have to make your antimatter in space, far away from the Earth, and use that for your starship construction. So again, it's not practical today, but it's not impossible.
The stars themselves suggest another possible solution to the propulsion problem. The energy released from hydrogen atoms fused together is what lights the sky across the universe. Since the 1950s, scientists have been developing fusion reactors to harness it.
The sun does it by brute force, has all that mass, squeezes all that hydrogen together to form helium, releases energy, and that's how the sun shines.
It's the holy grail of energy production. Tame the power of the sun and furnish humanity with an infinite supply of energy. But to get fusion going on Earth, you need to generate the heat of the sun. Upwards of 100 million degrees centigrade.
Well, we've achieved fusion on the ground. It's been done. Fusion happens when a hydrogen bomb is detonated, which is not what we want.
In the hydrogen bombs of the mid-20th century, the atomic explosion of a radioactive isotope was used to produce the heat required to achieve fusion. But that explosion of energy was not contained in a way that it could be harnessed.
What you want to do is be able to capture the energy source of the sun in order to heat your propellant or to use as propellant to get your spacecraft going fast enough to go to the stars.
Modern reactors achieve fusion by other means, by heating plasma. The problem with this approach so far is that the energy required to reach that heat has been greater than the energy produced by fusion. No reactor on Earth yet has even reached break-even. But at Princeton Satellite Systems, a team of engineers is on a mission to solve that problem and to build a fusion reactor that can take us to the stars.
My brother will tell the story that I'm the only person he knows that's actually doing what they thought they wanted to do in high school. I identified aerospace engineering. I picked colleges for aerospace engineering. I've been doing aerospace engineering ever since because it's really fun and challenging. Space is cool. The exhaust velocity that we have is only about 100 kilometers per second. And yet you can't get there fast unless you got some meaningful thrust.
Right, so you...
Aerospace engineer Stephanie Thomas is principal investigator in a NASA-funded program to build the world's first direct fusion drive,
Essentially, it's a straight line.
an integrated reactor and propulsion system in one.
We want to reach a neighboring star in the neighborhood of 5 light-years distance. We want to bring 10,000 kilograms of payload, that's 10 metric tons, and we need to do it with an exhaust velocity that we can actually achieve with an engine.
Thomas's first challenge is to achieve a constant flow of plasma to catalyze the reactor.
We're getting pulses, so we're pulsing current through these antennae. So every time we're running a 5 millisecond pulse, we heat the plasma, we generate current, you see a flash. But the reactor would be steady state. So instead of flashing like this, it would be bright all the time. So that's the goal.
Rather than using a heavy and hazardous fuel like uranium, the direct fusion drive runs on a naturally occurring isotope of hydrogen, deuterium, found all over the Earth in water. The drive unit is compact, at just 1 meter diameter and 10 meters long, small enough to mount on a spacecraft.
We think that we can build the next generation machine in maybe 5 years. It will take at least another 5 years to build a prototype that you could launch. But definitely 15 years at the outside, we think we could have one and put it in space. At some point, we have to visit the stars. We're never going to just sit here and be content, you know, even when we're visiting the planets, because we want to know what's out there. Everybody wants to go to the stars someday.
In the timeline of propulsion technology, that someday is getting closer. The next challenge in our bid for the stars is navigation.